Good afternoon to everyone. Today I am going to discuss about Hall effect sensors and their applications, which is one of the important sensors nowadays we are using in every application in our daily life. That is Hall sensor. So Hall effect sensor, through rooted in discovery made in 1879, continue to play a vital role in modern electronics, advanced measurement systems, and intelligent applications. Before we begin, let me give you a quick overview of what we will cover in today's session. The first one is motivation. Why magnetic sensing? What is the purpose of magnetic sensing? Then the second one is basics of Hall effect. After that, I will discuss about the types of Hall effect sensors. After that, I will discuss the interfacing and design considerations. After that, application across industries. After that, I will discuss the case studies and future trends. And finally, I will discuss few questions and answer session. Now, motivation by magnetic sensings. In today's world, the modern electronic systems requires precise, reliable, and contactless sensing. The concept of magnetic sensing, especially using Hall effect sensors, works even in harsh environment where optical or mechanical sensors fail. For example, to detect dust, oil, vibration, moisture, they are low cost, integrate easily with electronics, and can detect position, speed, current, and proximity, all without any physical contact. It is similar to a wireless sensor. The next point is basics of Hall effect. In this topic, we will discuss with the principle behind Hall effect, discovered by Edwin Hall in 1879. Here we will understand why a voltage appears when a current carrying conductor is exposed to a magnetic field. This simple physical phenomenon is the foundation for a wide range of modern sensors used in industries. Number three, that is types of Hall sensor. So Hall sensor come in different forms depending on the applications. We will cover in this topic. We will cover linear analog Hall sensor. In this sensor, the output varies continuously with magnetic field. Then we will discuss about the digital Hall sensor. So in this Hall sensor, the output is on off based on the magnetic threshold. And after that, I will discuss the current sensor. For this kind of sensor is isolated and high current measurement in power electronics and EV. Basically, it is used for high current measurement and power electronics and electric vehicles applications. After that, I will discuss the interfacing and design consideration. So in this topic, I will cover how to use a Hall sensor effectively. To do so, we need to understand its signal conditioning, biasing, temperature effect, and noise issues. We will also see how Hall elements are integrated inside integrated circuits, why offset and drift matter, how placement and magnets impacts response, what engineers must consider when embedding Hall sensors into large systems. After that, I will discuss about the application across industries. The biggest part of this talk this particular session focus on real engineering applications. Hall sensors are used everywhere in automotive system like ABS, then crankshaft application, then in motor and industrial automation, mainly in BLDC commutators, then in consumer electronics, like nowadays we are using smartphones, then laptops, then energy systems, inverters, then solar charger controller, many more applications like that, and also in robotics and medical devices. So we will see how multi-purpose and impactful these simple sensors are. Now, after that, I will discuss the case studies and future trends. So here I will discuss the practical case studies like how Hall sensor control BLDC motor, how they measure high currents in electric vehicles or inverter application. And I will briefly discuss the cutting edge trends like intelligent Hall sensors with on-chip microcontrollers, then automotive functional safety, then low power Hall sensor for IoT applications. And finally, I will conclude my discussion with some uh, by asking few questions with answer. Now, starting from in this slide, I am going to discuss about the motivation sensing the world around us. So every smart system starts with a sensing mechanism, and any intelligent or smart system can interact and interpret with a outside world. This perception is achieved through sensors which acts as the system's eyes, ears and other sensory organs. Without accurate and reliable sensing, a smart system is a blind element and unable to make rapid decisions to take appropriate actions. So sensors basically translate the physical phenomena into electrical signals that can be processed by the system's control unit. These physical quantities can encompass a wide range of parameters, including position, which determines the location of an object in space, then current, measuring the flow of electrical charge, then speed, accessing the rate of change of object position, after that angle, which determines the orientation of the object, and proximity, which detects the presence of an object within a certain range. The accuracy and reliability of these measurements are key factor to the overall performance of the smart system. Then next point is non-contact robust sensing is critical in harsh environment. In many applications, particularly those operating in harsh environment, traditionally sensing methods that rely on physical contact or are susceptible to environmental factors can be unreliable or even unusable. In harsh environment can include conditions such as high dust level. Dust particles can interfere with optical sensors and clog the mechanical components. Then oil and gas contamination, like oil and gears can coated sensor surface, affecting their accuracy and potentially causing damage. Then next one is mechanical wires and tears. Contact-based sensors are subject to wear and tear, leading to the reduced accuracy and eventual failure. Extreme temperature. Another point is extreme temperature. In high or low temperature can affect the performance of many sensor types. Then vibration and shock. So mechanical vibration and shocks can damage the delicate sensor components. Therefore, non-contact sensing methods that are robust and immune to this environmental factors are crucial for ensuring reliable operation in such condition. So non-contact sensing eliminates physical contact between the sensors and object being measured, reducing wear and tear and minimizing the impact of surface contamination. So robust sensors are designed to withstand in harsh environmental conditions without compromising their performance. To overcome such problem, the concept of magnetic sensor is very useful. So magnetic field based sensing, which is immune to dust, oil and mechanical wear. So magnetic field based sensing offers a compelling solution for application requiring non-contact and robust sensing. So this technology relies on the detection and measurement of the magnetic fields to interfere information about the object being sensed. What are the key advantages of magnetic field based sensing includes? The first one is immunity to dust and oil. Second one is non-contact operation. Third one is robustness. Fourth one is versatility. So what do you mean by immunity to dust and oil? So magnetic fields are not significantly affected by the presence of dust, oil, or other non-magnetic contaminants. This makes the magnetic sensor ideal for use in dirty or oily environment, mainly in oil industry, petrochemical industry. Then non-contact operations. So magnetic sensors do not require physical contact with the object being sensed, eliminating wear and tear and allowing the measurement through the intervening materials. Then robustness. So magnetic sensor can be designed to withstand harsh environmental conditions, including extreme temperature, vibration, high vibration, and shock. Then versatility. So magnetic field based sensing can be used to measure wide range of parameters, including position, speed, angle, and current. Hall sensor as a key enabling technology. So Hall sensor are the types of magnetic sensor that utilize the Hall effect to measure the strength of a magnetic field. The Hall effects is a phenomenon in which a voltage is produced across a conductor when magnetic field is applied perpendicularly to the direction of current flow. This voltage, known as the Hall voltage, is proportional to the strength of the magnetic field. Hall sensors are widely used in variety of applications due to their small size, low cost, and high reliability. They are particularly well suited for application requiring non-contact sensing in harsh environments. Some common applications of Hall sensor includes position sensing. So what is position sensing? It detecting the position of moving objects such as piston in an engine or robotic arm. Then speed sensing. So what do you mean by speed sensing? It measuring the speed of rotating objects such as motor shafts or a wheel. Then angle sensing. So what is angle sensing? Angle sensing determining the angular position of an object such as steering wheel or throttle. Then current sensing. So what is current sensing? Current sensing actually measuring the current flowing through a conductor. Then proximity sensing, it basically detects the presence of an object within a certain range. Now coming to the slide number 4, that is basics of Hall effect. The Hall effect was discovered by Edwin Herbert Hall, an American physicist in 1879. At the time, the electricity and magnetism were still developing research field, and many scientists were exploring how electric currents behave under magnetic forces. Hall was experimenting with a thin flat conductor while passing an electric current through it. He then applied a magnetic field perpendicular to the direction of the current, and he observed something unexpected. A small voltage appeared across the conductor at right angle to both the current and the magnetic field. So this voltage is called Hall voltage. Why is this surprising during that time? In normal condition, electron flows straight through the conductor, but when magnetic field is applied, the electrons are pushed sideway due to the Lorentz force. So this side push makes electrons accumulate on one side, creating a measurable voltage difference across the material. So this phenomenon was completely new at that time. In 1879, there were no electronic devices that needed magnetic sensing. So researcher considered it an interesting scientific observation, but did not see the practical use immediately. For nearly 70 years, it remained primarily a laboratory phenomenon used to study electric and magnetic field. Then the question is why it is important today. The Hall effect has now become a core principle in sensor technology and meteorology. It can used for characterizing materials. The Hall effect helps mean that this Hall effect phenomenon actually helps to determine the carrier concentration, that is number of electrons and holes. Scientists can identify whether a material is N type or P type, and it can measure the mobility or and other semiconductor properties. This is essential in semiconductor research and device fabrication. So this is comes under characterizing materials. Similarly, it can be used in measuring magnetic field. The Hall voltage is actually directly proportional to the magnetic field strength. This makes it a perfect foundation for making Hall sensor, then magnetic field meter, then current sensor. Okay. So another we can use the Hall sensor designing smart sensor. So modern Hall sensor integrate integrates the amplifiers, the filters, digital circuits, making them essential in automobile industry, consumer gadgets, then industrial automation, then robotics industry, then power electronics. What began a small accidental voltage detection has become a multi-billionaire dollar sensor industry. Now here you can see I have mentioned the types of Hall sensor. So the category is output based, the type is linear and switch, and the output pattern is analog and digital, and mainly it is used for for mainly linear type analog linear types Hall sensor basically used for field current and position sensing. Then second output based basically switch type, it is a digital sensor basically used for proximity sensing and speed sensing. After that, the digital type is three types. One is called unipolar type, then bipolar type, and third one is latching type. It acts as a switch on off state. The output is on or off, either on and off state. And basically, it is used for motors and detection. After that, application base also two types is current sensor and position sensor. It is the output of this two sensor, analog and digital, means we can generate analog and digital both kind of output, and it is used in power electronics and robotics and automotive industry. Then integration based Hall sensor. The type is Hall element and Hall IC. So the output is actually Hall element basically raw output. We'll get the raw sensor data, and Hall IC basically pre-processed. It will generate the output within a pre-processed manner. So it is ready to use. Consumer can use, industry can use directly. It is a ready-made data. Whereas the Hall element is a raw data, it can be used for research work purpose. And last one is advanced category. It is also two types, that is 3 axis and smart Hall sensor. And the output is both, for both cases are digital output, and it is useful in mobile sector, then wearable electronics application, then automobile industry. Next one is, so now I am going to discuss in detail about this based on output. So linear or analog Hall sensors. In linear and analog Hall sensor, the output is continuous analog voltage proportional to the magnetic field. If magnetic field increases, output voltage increases linearly and used when precise measurement of magnetic field position or current is needed. And what is the application? Mainly the current sensing application, then linear position measurement, then magnetic field mapping, then industrial control. So this kind of application is useful for this linear analog sensor. Then digital switch or latch Hall sensor. This sensor actually use sensor compare the magnetic field with an internal threshold and produce on-off output. So this types of this there are three types of such kind of Hall sensor. First one is called unipolar Hall sensor. So what is the function of unipolar Hall sensor? It detects north pole only or south pole in some versions. An output switch on when the magnetic field reaches in the threshold level. And what is the application? It is basically used for proximity detection, then open or closed door sensor, then flow meters. Next one is bipolar Hall sensor. It requires a north pole to activate and a south pole to deactivate or vice versa. Under fire, hysteresis is needed for noise immunity. What is the application? Application is speed detection, then sap monitoring. Okay. Then last one is latching Hall sensor, maintaining its output states until the opposite magnetic pole is applied. Works like a flip-flop controlled by magnetic field. What is the application? Mainly it is used in BLDC motor commutator, brushless fan, and rotary encoder circuits. Now come to the second application. Based on application, this is another type of Hall sensor based on application. I have shown few sensor diagram at the right hand side. I kept few picture and also some application where you can see it is very much useful for understanding purpose. I kept this image. So Hall, the first one is based on application, that is Hall effect current sensor. It is used the magnetic field generated by the current flowing in a conductor. What are the types? It is an open loop Hall current sensor and closed loop Hall current sensor. There are two types. One is called open loop Hall current sensor and second one is called closed loop Hall current sensor. So open loop Hall current sensor is very simple, fast and economical, and it measures both AC and DC current. Whereas closed loop current sensor, it is more accurate, use feedback to cancel the magnetic field and lower error and drift. What is the application of such kind of Hall sensor, current sensor? That is inverter circuit, then electric vehicle battery management, then power supply and SMPS, then motor drivers. Then second category of application based Hall sensor is Hall effect position sensor. It measures the linear or angular displacement by detecting the position of a magnet. Now the types. Linear position sensor. What are the types of this? Linear position sensors, then rotary angle sensor with rotating magnetic magnets, and absolute and incremental encoder. What is the application of this such kind of Hall sensor, position sensor? Mainly we are using this such kind of Hall sensor in joystick, then robotics arm application, then automotive industry, like gear position, steering position, then smart meters. These are the use of in this area. Then third one is another third one, another third application based Hall sensor is Hall effect speed sensors. So it convert rotating magnetic field into pulses. That is the function of this speed sensor. What is the application? Mainly it is used in ABS wheel speed sensor, then to control the speed of fan, then tachometers, then engine crankshaft or camshaft sensing. These are the application based sensors. Now coming to the types of this is the third types of Hall sensor, that is called integration based Hall sensor. So based on integration and electronics, you can see there are two kind of sensors that I have mentioned. One is basic Hall element and another one is integrated Hall sensor IC. So what is basic Hall elements? A simple Hall sensor chip that can produce Hall voltage, and it requires external amplifiers and analog to digital converter. And basically it is used in research and instrumentations. Okay, whereas in integrated Hall sensor ICs includes Hall element, then amplifier, then voltage regulator, then temperature compensation, then comparator for digital type, and output driver. Okay, so integrated Hall sensor includes these are the following elements. So where is the application such kind of Hall sensor? Mainly it is used in consumer electronics or consumer devices, then motor control, then automotive sensing. You can see I have mentioned one image, and at the right hand side I have mentioned here it is one Hall sensor, 3D Hall sensor was designed by Allegro Microsystem. It is a very renowned company. They are producing huge number of Hall sensor. 3D Hall sensor is US based company sensor. So this 3D Hall sensor, you can see for angle, it is useful for angle measurement. And the name of the number of the IC is A33230 230. A33230. Next, coming to the advanced kind of Hall sensor. This is also another types of Hall sensor. Okay, so the advanced and special Hall sensor, there are two different types. One is called three axial Hall sensors, and second one is Hall sensor with built-in microcontroller or digital signal processor. These are the very advanced nowadays. Most of the DSP application we are using this particular sensor. So what is three-axis Hall sensor? Three-axis Hall sensor actually detect the magnetic fields in X, Y, and Z direction and provide the complete magnetic vector information. What is the application of this three-axis Hall sensor? Mainly it is used in smartphones, then compass, digital compass, then wearable devices like our watch, digital watch, AI based watch, then robotics navigation. This is also this 3 axis Hall sensors are useful in this area, in this particular application. It is useful. Then the second type is Hall sensor with built-in microcontroller or DSP. So basically, it is a type of sensor, smart sensor with it's having on-chip calibration capability. Then it has linearization property, and the output of this Hall sensor is digital, and it can support I2C standard protocol, CAN protocol, SPI, then SEND protocol, and it is useful for diagnostic features also available, that is ASIL for automotive industry. And mainly this particular Hall sensor actually useful in electric vehicle industry, then space technology, okay, then robotics industry, then industrial automation application, then precision robotics, where very minute kind of analysis or experiment is required. For example, in medical robotics, where very small, precise surgery is required. In that particular case, this kind of Hall sensor is very useful, and it is called advanced Hall sensor, or sometimes it is called AI enabled artificial intelligence or intelligence Hall sensor. Now, interfacing and design consideration. So here, Hall element actually integration, Hall effect sensor are rarely used as discrete component. Instead of that, they are typically integrated into integrated circuit alongside the necessary signal conditioning circuitry. So this integration offers several advantages. The first one is miniaturization. That is what do you mean by miniaturization? Means IC fabrication allows actually for extremely small Hall elements and associated circuitry, leading to compact sensor packaging. Means all the items will be kept in a single small confined with one single IC. That is called miniaturization. Then improved performance. What is improved performance? The on-chip signal conditioning can compensate for temperature drift, then offset voltage and other non-idealistic behavior of the circuit, resulting in more accurate and stable measurement. Then cost effective. Mass production of integrated Hall effect sensor reduces the meaningful manufacturing cost. After that, next one is simplified interfacing. The interfacing is very simple. Integrated sensor often provide a digital or analog output signal that is very easily interfaced and with microcontroller or other electronic systems. So this integration processes involves depositing a thin film of semiconductor materials, example silicon or indium antimonide, onto a substrate. The Hall element is the pattern used using in photolithography, and signal conditioning circuitry such as amplifier, filter and temperature compensation circuit is fabricated on the same chip. Offset and drift consideration. So offset and drifts are two significant sources in Hall effect sensor. Offset means offset refers to a non-zero output voltage when no magnetic field is present. This offset can be caused by imperfection in the Hall elements or imbalance in the signal conditioning circuitry. And drift refers to the change in offset voltage over time or temperature. So temperature drift is particularly problematic because why? Because the Hall coefficient is temperature dependent. So several techniques can be used to minimize such type of offset and drift. First one is chopper stabilization, then offset cancellation circuits, then temperature compensation circuits, then calibration. Then next one is magnet placement and response. The placement of the magnet relative to the Hall sensor significantly affects the sensor's response. The magnetic field strength and direction at the Hall elements location determining by the magnitude and polarity of the Hall voltage. The first one is sensitivity. Sensitivity is maximized when the magnetic field lines are perpendicular to the Hall elements. Then linearity, the sensor response is most linear when the magnetic field strength is within a certain range. At high magnetic field strength, the Hall voltage may saturate. Number three, that is hysteresis. Hysteresis can occur if the magnetic materials exhibits hysteresis. This means that the sensor output will depends on the history of the magnetic field. So engineers must carefully consider the magnet's size, shape, and material when designing a Hall effect sensor system. Simulation can be used to predict the magnetic field distribution and optimize the magnet placement. Then embedding Hall sensor into larger system. When embedding Hall sensor into larger system, engineers must consider the several factors like power supply, then signal conditioning, then electromagnetic interference, then mechanical considerations, then environmental factors, then calibration and testing, then communication protocol, then software integration. So these are the parameters. So another important design consideration is noise consideration. So noise can significantly impact the accuracy and resolution of the Hall effect sensors. So mainly the noise source includes, what are the noise source are includes, that is first one is thermal noise, short noise, then 1 by F noise, which is called flicker noise, and external noise. So several techniques can be minimize the noise. Mainly, most of the industries are using shielding mechanism. Shielding can be used to protect the sensor from the external electromagnetic fields. Then filtering process, by using filtering, can be used to remove unwanted noise from the sensor output signal. Then averaging multiple measurement can be reduce the effect of random noise. Then chopper stabilization. Chopper stabilization can also reduce the effect of flicker noise, that is called 1 by F noise. Then proper grounding technique can minimize the ground loops and reduce the noise. By carefully considering this interfacing and design consideration, engineers can effectively utilize Hall effect sensor in a wide range of applications. So these are the application area where we can use the Hall sensor. Already I have explained. Just for your understanding, I have highlighted this particular slide. You can see. So the broader area is energy systems, then robotics and medical devices, then automotive systems, then motors and industrial automation, then consumer electronics. Now, this is the last slide in my presentation. That is future trends of Hall effect sensor. The field of Hall effect sensor is constantly evolving and driven by the increasing demand for high performance, low power consumption, and enhanced functionality. Here are some of the key trends shaping the future of Hall sensor technology. The first one is intelligent Hall sensor with on-chip microcontroller. So integrating microcontroller directly into Hall effect sensors enables advanced signal processing, calibration, and communication capabilities. This intelligent Hall sensor can perform complex tasks such as temperature compensation, offset correction, and linearization, improving accuracy and reducing the burden on the host microcontroller. They can also communicate with other devices via digital interfaces such as I2C or SPI, or simplifying the system integration. Then next one is automotive functional safety, ASIL. So automotive system become increasingly complex, functional safeties become a critical concern. So how Hall effect sensor actually used in automotive application must comply with stringent safety standards such as ISO 26262, which defines the automotive safety integration level, that is ASIL, which compliance require rigorous design, testing, and documentation process to ensure that the sensor can reliably detect and respond to potential hazards. And the last one is low power Hall sensor. In for IoT, mainly it is useful for IoT application. The proliferation of IoT devices is driving the demand for low power sensors that can operate for extended periods on battery power. So this sensor are being developed with the ultra low power consumption to enable applications such as smart home appliances, wearable devices, and industrial monitoring systems. So this sensor utilize advanced power management technique and optimize the circuit designs to minimize energy consumption without sacrificing performances. So thank you for your time. So this is my final discussion. So now I am concluding my session.